Okay, so 2 days ago, I already presented what we call WRF-comfort, which is a methodology we developed to compute, to estimate heat stress variables and the subgrid variability of this heat stress with a mesoscale model. So just to summarize, this is a method based on from one side, a series of larger simulation over a run simulation of a microscale, from which we derive the relationship between the mean wind velocity in evergreen cells and the mean wind speed and the variability as a function of the urban morphology. So we derived the three values of represented for wind speed in evergreen cells based on this relationship. And then, on the other hand, we computed fixed values of mean radiant temperature depending on the two main street directions that we consider in BEP-BEM. And then from this, we can build a set of 54 combination of these variables, from which we compute heat stress indexes. In this case, I chose UTCI and statistics of this. So 2 days ago, I presented the results, an example over Madrid. Now I will show you another example. In this case, you also saw other examples over Cyprus and Grenoble and Madrid for an historical series from Beatriz few hours ago. So now I will show you for Valencia. Valencia, as you probably know, is the third biggest city in Spain with a bit more than 800,000 people. Is in the south, is in the coast of Spain, so Mediterranean coast. A few information about the type of this type of the simulation we did with WRF. So before with the multilayer canopy parameterization BEP-BEM. So we use 3 domains, 9, 3, and 1 kilometers resolution. So this is the inner domain, Bujola-Carrera PBL schemes, and others. So we simulated 1 month in August 2023. And in this month, we have a heat wave. So the urban morphology, which is a very important information for this type of simulations, were derived from LCZ maps. So it's not very detailed yet. We will have soon much better data. But in this case, for example, here you can see a map of the LCZ. So for every LCZ, local climate zone, we have a well-defined set of morphological parameters. So in this case, for example, you see the blue area is local climate zone 2, which is the center of the city, very dense. Here, as an example, we have a picture of the street. So, for example, the morphological parameter we use there is mean street width of 10 meters and mean building height of 17.5 meters. So, narrow streets and dense city. Then, south of it, we have another region, less dense, classified as Z8, where we have, in this case, the morphological parameters. So the buildings are lower, just 1 floor, and the distance between the building is bigger than what we have in the center. In this case, the typical parameter we use is 32 meters as a width of the street. And then we have another type of morphology inland, which is the third pictures I put on the screen, as Z6 with again lower buildings but narrower streets, just for a point. Okay. So we as I said before, we ran 1 month. We validated the simulation. So this is an example of the validation for the 1 month. So here in red is the result from work, and in black the results of the measurements. So more or less the model follows the pattern measured of temperature at 2 meters in a station in the center of the city, with exception of one episode around the 10th of August, where for a few hours, for 1 hour basically, the wind shifted from sea breeze with inland breeze, and then we had a spike of temperature that the model wasn't able to reproduce. But the most important thing is the heat wave during in the last period of the month, and this is reproduced by the wind. So let's see now the maps. I picked one day of the heat wave. For example, on the left, top left, you have this special distribution of air temperature. So here is at 3 p.m. local solar time. So and the wind produced by the model. So here we can see, and I cannot really show, but okay, in the center of the city, maybe you can get here. So here is the center of the city. You see it's a bit hotter than here. Why this? Because here the morphology is the city is denser, so the wind is stopped, and the effect of the sea breeze is reduced. That's why we have higher temperature there than just south of it. But the biggest feature that we can observe in terms of spatial distribution of the temperature is from the coast to inland, mainly due to the impact of the sea, and we see the maximum temperature were simulated inland of Valencia. Now let's look at the heat stress. So here, as I said before, since I can compute the statistics of subgrid values of UTCI, so the heat stress in grid points, I can plot the values of what they call a cool spot, which is basically this time of day a point in the shadow, and what they call a hot spot, which is basically a point that is the maximum of the worst heat stress that you can have in the region. So let's look at the cool spot. Here we can clearly see that the maximum in the city are in the city center, and the local values around, and the highest UTCI values are here. If you look at the maximum at the hotspot values, we can see here that we have why that is, because here we have a lower space, and we have a shadowing effect, and that's why we have a lower heat stress, maximum heat stress here in the center, in our space, and the south of the city, buildings, so the sun can penetrate. If you look at during the night, the maximum both of air temperature and heat stress values are in the city centers. This is mainly due to the fact that, as I said before, the streets are narrower, so much more trapping of radiation and the heat. And now the minimum temperatures are inland, where before we have the maximum temperature. And this is again due to the effect of the distance from the sea. Okay, that's for air temperature for outdoor, but as we said, somebody said this morning, people spend 90% of the time indoor. So I thought, okay, what's happening indoor if we don't have the possibility to control the temperature indoor, if we don't have air conditioning here? So, I don't know if you know, but with the building energy model that we have been working in the multilayer urban canopy parameterization, we compute the indoor temperature with the aim to estimate, if you have air conditioning, the amount of energy consumptions and the amount of anthropogenic heat that we eject outside. So I said, okay, what's going to happen if we turn off the air conditioning. So I can still run the same building energy model, but without control of the indoor temperature. So the indoor temperature is free to sorry, is free to fluctuate in a certain sense, following the energy balance of the building. So then the next question was, how can I evaluate if the indoor temperature is in a comfort range or not? I was speaking about this with a student from the University of Cyprus that was visiting me, Giandomenico Burro, and he put me in contact with his professor, Salvatore Carlucci, who is an expert on indoor sport. So he told me that there is a adaptive model, that's what they call, that based on a running mean of outdoor temperature, can estimate the range of comfort for the indoor. So this is the formula we use to estimate the running mean of the outdoor temperature, which is basically a kind of average temperature of the previous week, more or less. And then from this, we can define with the formula that I put at the bottom, which is a range of comfort in terms of temperature for the unit. So I said, okay, we know this. So I set up a simulation without air conditioning, but with two ventilation conditions. One with windows closed, so a ventilation rate of 0.5. So every 2 hours we exchange all the air that is in the building in the room. But when the outdoor temperature is below this comfort threshold, we assume that the people open the windows, so increase the ventilation rates, and to exchange, to renovate the indoor air every year. So then I ran the code, the simulations. What are the results? So on the left, I still put the air temperature outside, but on the right, on the top, we have the indoor temperature in the lowest floor. So I can differentiate between the different floors. So in the city center, we have buildings of 3 floors. And we can see that for the first floor, for example, now we have a minimum in the city center because it's the only place where the first floor is as another floor on top. All the other regions are all the buildings are just one floor, so they have a higher temperature. If we look at the third floor, which is present only in the city center, we have higher temperature than in the lowest floor. So what I want to show with this is that the indoor temperature may have a different spatial distribution than what you can see in the outdoor temperature if you don't take into account the building structures and the floors. During the night, again, now the worst conditions are in the city centers, both for the lowest floor and the top floor. Then say, okay, these are the temperatures, but what's the difference compared to the comfort range that I mentioned before? So on the left now we have the spatial distribution of the comfort temperature for indoor derived from the running mean of the outdoor temperature, and we can see that since the center is usually hotter, so this comfort temperature is hotter in the center than in the rest of the city. Then I plot on the right the difference between the indoor temperature and this comfort range, and we can again see with even more is even more clear that the first floor in the center is in a better thermal condition than what we can have outside. But in this better condition also is the third floor, which is receiving more radiation. And during the night, is again more or less the same tendency as I said before for air temperature, still with a worse condition in the city center. Here I put a time evolution to show how this indoor temperature fluctuates. On the left, the black line, but in these 3 graphs, which are in the 3 points I indicated before. On the left is the center. On the center, the south part of the city, low density, and on the right, the point inland. The black lines are outdoor temperature. The red line is the indoor first floor. The blue line is the third floor or top floor when you have it, so just in the city center. And the green line is the comfort temperature derived with based on a running mean of the outdoor temperature. So we can see that all the time we are outside the comfort range in this case. So clear demonstration of air conditioning is needed in Valencia. And again, another thing that I found interesting is that even if they open the window during the night, because during the night the air temperature outdoor is below the comfort range, the indoor temperature doesn't cool enough. This is something similar to what I don't remember a girl showed 2 days ago for the Netherlands. They have measurements indoor, and they also see that the air temperature in the night doesn't cool. Then it said, okay, what about if I start to study some strategies? For example, one strategy could be to put trees in the streets. So I introduced a simple parameterization of the effect of trees in BEP-BEM. Just taking account the impact on shortwave radiation, and assume that all the streets in Valencia are covered by trees at 70%. So 70% of the streets in already itself is with trees. So what's the impact on this? So impact on temperature, air temperature outdoor, quite small, less than 1 degree, between 0.5 and 0.7. But the impact on UTCI, bigger. Okay, on the top figure, you see, so these are different between the values with simulation with trees minus the base case. So we see that in the city center with narrower streets, the impact is smaller because the fact that the streets are narrow already generates some shadowing. While in the other part of the city, which lower density, the impact of trees is much bigger because the shadowing and the generates is bigger. But the interesting thing is that we see an impact also, I saw an impact also on indoor temperature on the first floor. I forgot to say that for me the trees are a crown between 5 and 10 meters. So they make shadow on the first floor. So we see a reduction in indoor temperature, even in indoor of more than 1 degree, but just for the first floor, not for the third floor, which is outside of the above the figures. And if we plot now I plotted the time evolution, we can see that still we are above the comfort range, but if you look in, we reduce the maximum peak in particular for the indoor temperature for the first floor too. Okay, now just to conclude, so the message I want to give in this talk is that the spatial distribution of air temperature may be different than the spatial distribution of heat stress values and the spatial distribution of indoor temperature. So it's really important to account for the urban morphology, which is a key parameters that enters in this distribution, and for a city like Valencia, which is coastal, the distance from the sea. So it's a combination of the urban morphology and the geography that generates the breeze. And at the end, just a reminder that so now we have this tool, which is a WRF-comfort, we can use, and we can challenge it in a certain sense to see how we can test it and improve it. Okay, thank you.